to 3-1, which is going to be our exponent and log basics. This is just going to be a quick review. You'll have notes to refer to as well, and discussions in class. But if you're absent, this should be fairly adequate for going over the fundamentals. An exponential function with base b is in this form right here, a b raised to the x power, where x is any real number. But very importantly, our b has to be positive, greater than 0, but not equal to 1. If we're equal to 1, we just have basically 1 raised to any power is going to be 1. So that doesn't really serve any purpose. This a can reflect across our x-axis. It can stretch, it can compress. And we could do things to this x that would also stretch and compress and do some other things. But that's going to be our basic form. So real quick, some examples are these three right over here where we have 4 to the x, and this is the parent function of 4 to the x power. So parent functions, when we have this, is b to the x, where b is going to be any real number. It can be 2 to the x, 3 to the x, 4 to the x. Each one will have its own unique parent thing that we transform from there. So 1/3 of the x, this can absolutely be a fraction, and this can have a negative right here, and this can easily be written as 1/7 to the x power as well. None examples, we have a quadratic, quickly recognized. Here we have a constant. We just have a number raised to another number. And here, well, it doesn't serve any purpose. You could get philosophical and say, well, it looks exponential. It falls exponential, but it's just going to equal to 1. It's going to be a constant, all right? So we're going to talk briefly, but our basic forms of our graph are going to be this kind of growth, rapid growth, or this rapid decay type of characteristic. We can stretch, compress, and do some other things to them. But when b is greater than 1, you're going to have a graph that looks sort of like this. When b is less than 1 but greater than 0, it's going to come down like this. So they're going to be our growth and decays, which we'll look at in a moment. I want to compare what exponential and logarithmic. The relationship is that of an inverse. They are inverses of each other, okay? So we have our exponential function, y is equal to 2 to the x. If we were to deflect that over y is equal to x graph, you're going to get its logarithmic. And that graph is going to be x is equal to 2y. We'll review the log rules here, or the log relationship here in, I think, the next video. So let's just take a look at a couple more basics, exponential growth and decay. Some teachers teach it differently than others. I actually have kind of both of them up here. This is the one that I prefer. I tend to go thinking this way. When b is greater than 1, so that b right there is greater than 1, you're going to have a growth. And notice how it crosses at 0, 1. They will all grow. All parent functions, unless there's a translation going on, is going to cross at 0, 1. Because think of it, b to the 0 power is going to equal to 1. So it doesn't matter what that base is, 2, 7, 23, negative, I mean not negative, but 1/3, whatever, it's going to be 1. And this is going to cross at 1b, because when I put b to the first power, it's going to equal to b. All right, so that'll be my output. And the same thing going on over here. Yeah, it's going to be a fraction, but you're still going to cross at these points. So this will be a decay. When you have 1/3 to the 5th power, that's a very small fraction. It's going to get very close to this horizontal asymptote. Some teachers put it with a negative sign right here, and that's perfectly fine. This is nothing more than 1/2 to the x power, right? So that's what's going on here. So I'm indifferent if you want to write it that way, and I probably will write it that way a few times because a lot of application problems do this, especially in the finance world. You're going to see some of that, and well, a lot of application problems do that actually. All right. So here's another important property, 1-to-1, property of exponent functions, as you can see, for b greater than 0 and not equal to 1, standard writing for an exponent. B to the x is equal to b to the y, if and only if x is y. Now remember, a good mathematical definition, if you remember from your geometry, is biconditional. The conditional and its converse must be true. So if x is equal to y, then bx is equal to by. Simply put, if the bases are the same, you can set these two things equal to each other. 2x is equal to 4, x is equal to 2. Pretty straightforward. If they're not the same, see if you can get them to be the same. So this is just 4x plus 2, but this is also 4 raised to the second power. That's 16 times x minus 3. So you have x plus 2 is equal to 2x minus 6. Subtract x, add 6, you get x is equal to 8. So this, sometimes you got to think about this. Now there's a couple ways to do this. You could think of this as 3 to the negative 1n is equal to 3 to the negative 4 times 2/3. That's probably the way I would probably end up doing it. You could have done 1/3 to the n is equal to 1 over 3 to the 4th to the 2/3, but that's a little bit harder to solve. You can just set these two things each equal to the other, so you have negative n is equal to negative 8/3. So n is equal to positive 8/3. All right. Okay, so one last thing, we want to talk about our natural base. This is massive in the real world, in finance, in science, in your biology classes. It's going to pop up constantly. And if you take calculus, if you choose to take that course, most likely in college, it's going to be pretty much part of many of the work you're going to do. So let's just talk real quick about n, and then we'll finish this lesson and get on to part 2 in a moment. N is just one of those cool numbers that mathematically, if we have this equation, this expression here, 1 plus 1 over n raised to the n power, this is an exponent. What's going to happen is as we increase n to bigger and bigger numbers, it's going to start approaching 2.718 something. It's going to get very, very close. And that is going to be this, what we call our horizontal asymptote in this case. But what's interesting is later on in this course, we're going to briefly talk about polar and polar geometry, basically. And if you were to do graph this function, here's y is equal to e to the x. Basically e, 2.718 blah 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 to the x power. Here is our parent function right here. And it's a nice good graph. And you notice it crosses at 0, 1 just like all the others. All right. And at 1, 2.7 something just like all the others. So it behaves just like all the other exponent functions. But if we were to transfer it to polar, you're going to start getting this really cool spiral. This pops up in nature constantly. You think of the nautilus, of the pine cone, of so many different things. Water movement. This is a huge deal in mathematics. So all your future math classes, get used to this. It's going to pop up everywhere. If you were curious and looked at one of my calculus videos on YouTube, I actually discuss the limit of this right here. As x approaches a bigger number, it will approach e. That's what that's actually a very core pre-cal concept that we'll probably get into much later in the year. So these just pop up constantly. So we're going to integrate natural logs in a lot of our work. Alrighty, so I think that pretty much wraps it up, and I'll get this posted and on to the next video.